So let's look at grounding-based bots. So grounding means that you have a bot that has access to some kind of knowledge base. And nowadays, the most widely used technique is having access to a knowledge graph. You can see that this pattern approach has its limit. If you want to be able to answer a large amount of questions on different topics, you would have to hand code them, all of them, into patterns, asking about countries and cities and universities, and making a pattern for every possible question would just not be feasible. So rather than doing this, the idea is that you have a knowledge graph available. And the new thing that you need now is to be able to translate a natural language question into a query that retrieves the answer from the knowledge graph. And a very simple way of implementing this we have done in a lab exercise, right? So you could have a question like, what is X? Where you recognize this kind of question with a pattern. So this is asking for a definition, basically, like in what is Concordia University? And then you generate a query to DBpedia to get the comment in the language of the current user for X, and then you get an answer that looks like this. And you have seen that this is basically what Google retrieves as part of the answer when you ask it a question like this. So the general workflow of a bot is to first analyze the question. Can be simple using patterns, or more typical, applying some natural language processing on it. So this way we find out what's being asked. Then we generate possible answers. So in natural language, you always have ambiguity. So there are different ways of identifying the question, of formulating queries. So in many professional systems, you don't just generate one answer, you generate multiple possible answers. You score them, like I showed you earlier, possibly by comparing to the question. And then you return the top scoring answer as the output of your bot. You have done Sparkle, and you know that for different type of questions, you need different Sparkle query structures and constructs. Yeah, you might need the ask or a select. You might need some kind of grouping, counting, aggregating, computing the sum, and so on to be able to answer a question. So being able to generate the right query for a question is actually quite tricky. And one way of making this feasible is to first classify the question. So if you have a lot of example questions, you can categorize them. And then for the specific category of question, you can have one or multiple Sparkle query patterns that you use. So this way, it becomes a lot more manageable, because first, you know what type of question it is. And then second, for each question type, you can have different ways of extracting the information and putting them into a specific Sparkle query. So in other words, you don't try to generate the complete query from scratch. You have kind of a number of existing Sparkle queries that cover certain question types, a predefined query for locations, for definitions, for persons. And when you recognize that the question is of this type, then you apply some processing on the text, fill in the variables in the Sparkle query, and return the answer. So here are some example question types. For example, asking for a person, asking for a location, asking for an organization, for a point in time, for a duration of time, for an amount of money, and a few more, asking for a percentage, asking for an amount, asking for a distance, for a description, asking for a title, a definition, or basically anything else that doesn't fall into your other predefined categories. So now, based on the example questions, how do you find the category, the question type? Well, this we also covered in previous lecture, this is a typical machine learning problem. So this is a classification problem. So we need a classifier where we input the question and we get the category, the question type as output. So we need some training data, a lot of example questions where we have the label available, knowing that this is an amount question, this is a distance question, and so on. Then we need a machine learning algorithm. You learned some of them, and in a machine learning course, you learn a lot more. And then we can train this algorithm, and for every new question, we can generate the label. So here we have the additional challenge that the input is a natural language text, the question that comes into the bot. And the machine learning algorithms all expect some kind of input feature vector. So we've seen one way of converting natural language into a feature vector, which was the idea of a TF-IDF vector. The downside is that this results in a large number of dimensions. Remember how this works. If we generate these TF-IDF vector, they have as many dimensions as we have words in the vocabulary. And whenever you have so many high dimensions, it's very tricky in machine learning to train the algorithms because you don't have enough data available for all of these dimensions, and this results typically in overfitting. So what you do in practice is to have some kind of dimensionality reduction. Essentially, we want to have a lower dimensional feature from the input text. So there are different ways of doing this. We'll talk about deep learning techniques later on in the course. The classical techniques here are basically a number of strategies for converting the input into a feature vector. For example, we could look at the length of the question as one feature. How many words or characters are there? So this is one dimension. We can look at how many words have a capital letter. This could maybe ask for a definition. And again, this would be a second dimension. We could look at specific punctuation marks, like is there a question mark at the end of the not, at the end of the question or not? So this would be a third dimension. And so on. So you can look at various possible features. And this way you would represent an input question not with a vector of 1,000 dimensions, but just 5 dimensions. So the tricky bit obviously is to find good features that help in classifying. So this is very domain dependent. To give you a small example and understand how this could work, on the worksheet, try out tasks 3 and 4, and then I'll see you back in the next lecture part.